And some of the random states you could take pictures with, and other of the random states you could not take pictures with. And it was called the dice chip. So it was just like, roll the dice. Are we going to be able to take a picture this time? Sometimes the only thing you do is power it down and start over again. It's a prototype device. Why did I do that? Okay, it's this one I want to make big. Okay, slide 13. And you notice I'm actually calm with. Okay, so we wrote down the transforms over there. We decided that this was 3, and I wouldn't write the U of t down. This is minus 5 e to the minus 1t. And this was sine, oh, what was it? It was, I have to get that one right. Sine omega t is omega over s squared plus omega squared. Okay, so that's telling me my omega here is 2. So this is sine 2t. Now I need to have an omega on the top. So my omega was 2, so 6 is really 3 times 2. So this becomes 3 sine omega t. I left the u of t off because the standard form for doing this is at the end when you do the reverse inverse Laplace transforms is you multiply the whole expression by u of t. Just to remind you that you have no information about this for t less than 0. And that will force the function to be 0 for t less than 0.
Another question.
Yeah.
For the sine of omega t, is it sine of omega multiplied by t, or is it sine of omega t?
It's sine omega t, and if you look at the transform thing, this is omega squared. So the omega that I'm going to put in there, which becomes a 2, is whatever the square root of this number is. Fun with tables. And then I've got to have an omega up on top too. So I've got to change the 6 into 3 times 2. Yeah.
Would you always divide the numerator by 2 and put it in front of the sign?
No, because let's say if there was 9 here, if this was s squared plus 9, then it would be sine of 3t, and I'd have a 2 out front. Yeah, so just be careful with this because, we'll talk about that. Yeah. Okay. We got another one here, 1. The delta of t transforms into 1. And I'll write this one down again, and hopefully it won't crash. E to the minus alpha t becomes 1 over s plus alpha. And then I've got something that looks like a cosine. And my this is a lot of this is practice with tables. Start on the homework early. I will be in my office most of the day tomorrow and Friday. I'll answer emails if you have questions on it. You should have everything you need to do the homework. And again, this one's kind of a long homework because Laplace transforms get used a lot in the curriculum. You will have more classes that involve them. So this delta of t, this 1, when I'm transforming it back in the time domain, becomes delta of t. The 3 over s plus 4 is just going to be 3e to the minus 4t. Now I got lucky with this one. My omega is 5. So omega squared is 25. Omega is 5. Oh, but I've got the 5 out front. But all I need up on top on this one is an s. So this is going to be minus 5, because there's a minus sign on it, over cosine 5t. And then I go through and I multiply the whole answer by U of t to make it mathematically correct. Okay. I don't do all these slides today, thank goodness. So there it is, the solution. Okay, you got my opinion on these. I added these in today. If you want to find the inverse Laplace transform of something where the denominator has a bunch of terms factored out, there's nothing in the tables that look like that. You could probably find a calculator online that would give you the answer, but you wouldn't really kind of know how you got there. The way you do this is we have to do a partial fraction expansion. We know this whole fraction here, f of s, is going to be some variable, we just call it a, over the first factor, s, b over the second factor, s plus 2, and c over the third factor, s plus 3. I'm actually going to try to pay attention to the chat because this is an EE110. Yeah. It didn't show the third method. Yeah, I'm not surprised. This is the pre-lecture quizzes were written a long time ago, and I don't have the source code for them, and they don't get me started. In NAUITS. Okay, so there's 3 methods we're going to talk about. Some of them more than others. My favorite way to do these partial fraction expansions, because this is the easiest way to do it, and it's the way you're going to be less likely to make mistakes, is the best one's the residue method. It's quick. Once you know the formula, you can knock them out really fast. This algebraic method, it's in the slides, but I've been skipping over them for the past 3 years. For people who really love algebra, you may want to do that, but I don't recommend it. Everyone who tries using the algebraic method on the exam almost always gets the answer wrong. And I usually don't even try to grade your algebra. I just look at it and go, okay. I get a feel for whether I think you could have possibly solved it that way or not, and base your score on that. The other method that I like a lot is the substitution method. We'll finish the slide and then I'll reboot. The substitution method is a way of finding the rest of the terms when residue fails. So between residue and substitution, you can pretty much find any one of these. And we'll go through a